Hello pre-calculus, welcome back. In this video, I'm going to talk to you about graphing the secant and cosecant functions. And the way we're going to do that is actually pretty cool. We're going to exploit the relationship between secant and cosecant and sine. So because secant is equal to 1 over cosine x, when we're trying to graph secant, we can accomplish that by sketching the graph of cosine. And when we have cosecant, because cosecant is equal to 1 over the sine of x, when we want to graph cosecant, we can exploit the graph of sine of x and kind of sketch that and help us here. So that's why I included at the top of this video these instructions here. This tells us how to graph sine and cosine. And so to graph secant and cosecant, we're just going to have to use these same methods, and then we have an additional step at the end to graph our cosecant and our secant. So it's nice because it just adds one additional step to how we've already been practicing our graphs, and I think that's kind of nice. So we're going to start off. The first example we're going to do is we're going to graph the secant function, and I'm going to give us a very specific example. So what we're going to do for secant is we're actually going to graph this following function. We're going to graph one period. Whenever you say graph a sinusoidal function, it's always understood to mean one period. And we're going to graph y is equal to 3 times the secant of 1/2 x minus 1. And to do that, we're going to first sketch, I spelled sketch wrong, sketch the graph of y is equal to 3 times the cosine of 1/2 x minus 1. And then 2, we're going to use our sketch to graph the secant. But I'm going to show you why this works. I have a nice little thing set up on Desmos that I think will show you what we're talking about here. So here I've included our graph of secant and our graph of cosine. So this is our graph of cosine. We're familiar with it at this point, I think. We have a point at 0, 1, a point at pi over 2, 0, and a point at pi negative 1, and 3 pi over 2, 0, and 2 pi 1, right? That's one whole period from 0 to 2 pi of our cosine graph. So let's think about this, because we know secant is 1 over cosine. So one interesting thing about the graph of secant is anywhere where I have cosine equal to 0, I'm going to get undefined on my secant graph. Let me show you what the secant graph looks like here. So this is the associated secant graph that goes along with this cosine graph. And I want to show you what I'm seeing here that makes this so cool. So let's look at secant by itself for a second. What a strange graph. Kind of looks like two different hands reaching towards each other, about to interlock fingers, I think. A lot of times students will call this shape a parabola. It's not a parabola, it's a secant. But I understand why you say that. The shape does look very similar. It does look very similar. I will call it a U shape. But it's not a parabola, it behaves differently. One thing is we have those asymptotes I was talking about here. Like, take a look at this green line here is an asymptote. And I have periodic asymptotes. So I have one here, 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 here. We'll talk about this formula I created in class. So we have asymptotes. Parabolas don't have asymptotes, but the secant graph does. And now I want to look at both of them together. So take a look here, where cosine and secant are kind of glued together. Everywhere I have a peak or a valley of my cosine graph, that's glued to the bottom of my U shape there. And everywhere where cosine is equal to 0, I have an asymptote. And all I really need to be able to graph secant is I need to know where the bottom of the U is, and I need to know where my asymptotes are. And once I know that, I will totally be able to graph this thing. And watch what happens, even if I do a phase shift. Look, my cosine went with us. Even as I shifted the phase, the maximum and minimum values of cosine are still telling me where my U belongs. And the 0 is still telling me where my asymptote belongs. My formula's off now because I phase shifted it. But yeah, so take a look. No matter where, even if I shift it this way, I can change my A value. It's kind of trippy when I do it like this. I promise I'm not hypnotizing you. I can change my A value. No matter what I do to this graph, I always have the same situation. I always have that the U is glued to my cosine. And wherever I have a 0 on the cosine graph, I have an asymptote on my secant graph. So what we're going to do is we're going to sketch the graph of cosine, and everywhere where I have a maximum or a minimum, that's where my U is going to touch. And everywhere where I have a value of 0, that's where I'll have an asymptote. So I'll be able to sketch in those points. Let's try the example. I think that'll help. Hopefully this visualization helped you guys a little bit. So let's try it. The first thing we want to do is we want to sketch our graph of the associated cosine. So notice what I did here. I kept my A value the same. I kept my B value the same. My C value, I don't see a C value. There's no C in this one. But I kept my D value the same. The only thing I changed was I changed secant to cosine. So this is the associated cosine that goes along with my secant graph. And when I graph this, I will be able to tell you everything you need to know about that secant graph. So let's review our instructions for what we're going to do here. To graph this cosine, we're going to find our amplitude, our period, our phase shift, and then we're going to shift the graph to the left or right by C over B and up or down by D. So let's find our amplitude and our period, and then we'll be able to handle this. So excited, you guys. Let's check it out. This will be good practice for those of you who are still struggling with how to graph the cosine as well. Okay, so let's tackle that. We're going to do, step 1 is we're going to look at this cosine graph. So here's what we're going to do. We're going to sketch the graph of that cosine. Cosine of 1 over x minus 1. And to do that, our first step is to identify that our A is equal to 3. This is going to tell us the distance of the midline here. The next thing is we're going to figure out our period, which is equal to 2 pi times the absolute value of B. So in this case, oh, I wrote 1 over x. What a typo. What a terrible typo. Let me fix that, you guys. 1/2 x. Sorry about that. Our B value is 1/2. So we have 2 pi times 1/2, which gives us pi. So the period of our graph is pi. Yeah. And then we're going to sketch this graph. Oh, let's talk about the phase shift. Let's not get ahead of ourselves. We're supposed to find, do we have a phase shift? C over B. So what I notice here is that my C value, there is no C value. So that makes my C value equal to 0, and my B is equal to 1/2. So 0 divided by 1/2 is equal to 0. So there's no phase shift, no horizontal shift, which is kind of nice. No phase shift. But I do want us to note we do have a vertical shift. That D value is -1. So we're shifting this entire graph down by 1. But our first move is we're going to want to just graph it, and then using our period, and then we'll go ahead and shift it down by 1. We're going to use our period and our amplitude. So let's sketch that graph here. So I know that it's going to take me 1 whole pi to graph. So I'm going to look at this as pi over 4. And I'm going to look at this as pi over 2. And this I'll make 3 pi over 4. And this here I will make pi. And so that puts 0 right there on my x-axis. Let's draw this really nice. And I remember that my amplitude is equal to 3, and that I have a vertical shift to worry about. So I'm going to give myself at least 4 little tick marks. So here's 1, 2, 3, 4. Here's 1, 2, negative 1, negative 2, negative 3, and negative 4. So right now, what I'm sketching is, in essence, the graph of y is equal to cosine of 1/2 x. Or sorry, y is equal to 3 times the cosine of 1/2 x. And then after I do that, I'll shift the whole graph down by 1. So I know at 0 that my cosine is equal to my amplitude. So that gives me a point at 3. And then here's what we'll have at pi over 4. We'll have a 0. At pi over 2, we'll have a negative 3. At 3 pi over 4, we'll have another 0. And at pi, we'll have a value of 3. So this is kind of my sketch of 1 period of cosine. But this is this graph here. Remember, the graph we're looking for has a downward shift of -1. So that means I'm going to move my midline on my graph, which right now is the x-axis. Going to shift that midline down by 1. And all of these points I'm going to pull down by 1. So this point at 0, 3, I'm going to pull that to 0, 2. This point at pi over 4 is 0. I'm going to pull that to pi over 4, -1. And that's what I'm doing in all these places. I'm just pulling my graph down by 1. By 1. And I've shifted that entire midline down. So now I'm going to erase the graph in white. That was really there just to help us accomplish our transformation. So let's get rid of that for clarity's sake. And I'm going to sketch my cosine graph in here. And here's where the magic happens. This is a beautiful cosine graph, but we're trying to graph secant, right? That was our goal. And I know that everywhere my graph touches the midline, so everywhere my graph is touching that midline, I'm going to have an asymptote. So I'm going to go ahead and graph our secant in green. So we're going to have asymptotes here because my graph is touching my midline, and here because my graph is touching my midline. And then at each peak and valley, that's going to be the base of my U shape. So I have a U shape here. And a U shape here. And a U shape here. So in green, I actually have my secant graph. We can get rid of that cosine graph. Thank you for your help, cosine graph, but we don't need you anymore. Now I have my beautiful secant graph. Isn't that nice? And we don't even have to work that much harder than usual. We don't even have to work that much harder than usual. Notice I only drew half of a U shape. You could fill it in the rest of the way if you like. You could say, I see that symmetry demands that I have another asymptote. 1, 2, 3, 4, right here. You could see that. That symmetry demands. And you could write the full U shape. But you don't have to. For my purposes, as long as you have one full period of the graph, I'm a happy camper. I'm a happy camper. I hope that was helpful to you. I can't wait to show you the next. So that was the graph of secant. That's how we did this. The nice thing here, now we're going to take and we're going to attack cosecant. And we're actually going to be able to do the same exact method. It's going to be lovely. So let's go hop over to Desmos, and I'm going to change a couple things. So we want to talk about cosecant. So instead of secant here, I'm going to talk about cosecant. Let's change it. We're going to talk about the cosecant. So that's what the cosecant looks like. And cosecant is not related to cosine. Cosecant is related to sine. So I'm going to change that graph here. And take a look at what's happening. Now here's our beautiful sine graph. You can see that. And take a look at cosecant. Why? It has the same relationship to sine. Cosecant has the same relationship to sine that secant has to cosine. Everywhere I have a peak or a valley, that's where I glue my little U shape. And everywhere that I have a 0 on my sine function, I have an asymptote. Let's take a look. X is equal to 1.5. There we go. Isn't that amazing? So we're going to be able to do the same thing when we're trying to graph cosecant. We're going to graph an associated sine function. And then everywhere that we have a peak or a valley, a maximum or a minimum on our sine function, that's where our U is going to be glued. And everywhere that we have a 0, that's going to give us an asymptote. And this works the same way. It doesn't matter if I shift my sine graph up or down. I have asymptotes wherever my graph touches my midline. It doesn't matter if I do a phase shift. The asymptotes travel with the peaks and the valleys. I hope seeing this is helping you. But even if it's not helping you, it's definitely entertaining me. I love looking at this. I think it's beautiful. All right, so let's do one example. The nice thing is it's going to be very similar. So we're going to graph cosecant this time. And so how we're going to do that, we're going to graph the associated sine function and use that to sketch. So let me show you. So we're working with cosecant now. Let's do an example. So graph the cosecant, graph this here. We're going to do y is equal to -2 times the cosecant of a 2 over pi x plus 1 over pi minus 2. So what we're going to do is we're going to follow the same steps. We're going to graph the associated, in this case, we're going to graph the associated sine function. And then we're going to use that sine function to graph the cosecant function that we want. So let's start off by figuring out what that associated sine function is. Notice again, all I'm changing here is the cosecant. I'm changing that to the sine. My a is -2. My b is 2 over pi. My c is 1 over pi. And my d is -2. So let's go ahead and follow our steps here for graphing our sine function. First thing we want to do is identify our a. Here, my absolute value of a is equal to the absolute value of -2, which is 2. But remember, when a is negative, that's going to cause a reflection of our graph. So let's keep that in mind as we proceed. The second thing we want to do is find the period, which is equal to 2 pi times the absolute value of b. So here we have 2 pi times our b value is 2 over pi. So my pi's will cancel, and I'll end up with a period of 4. We want to identify our phase shift, which is c over b. So in this case, our c is -1 over pi, and our b is 2 over pi. My dog's going nuts. I'm sorry, guys. -1 over pi times pi over 2. So our pi's are going to cancel, and we're going to end up with a phase shift of -1/2. So remember, this is our phase shift. This is horizontal of -1/2. And we're almost ready here. We're almost ready here. I want us to pay attention to our d. In this case, our d is equal to -2. So we're going to have a vertical shift of -2. So this is all the factors we have to work with. The things I'm especially trying to keep in mind, my amplitude is 2. Because a is negative, I'm going to have a reflection across my x-axis. I'm keeping that in mind. My period is 4, and my phase shift is -1/2. So here's how I'm going to set up my graph of the associated sine function. My period is 4, but I have that shift of 1/2. So I'm going to be a little bit cautious here in how I set up my x and y. And I'm going to say this distance is 1/2, and this is 1, and this is 1.5, and this is 2, and this is 2.5, and this is 3, and this is 3.5, and this is 4. And then so that would make this -0.5, and that would make that -1. And I know my amplitude is 2, but I'm going to do some vertical shifting in here. So I'm going to give myself room to shift, room to grow. So 1, 2, a 3, a 4, a 5. And then here we have a -1, a -2, a -3, a -4, a -5. So I'm going to take a look at what this graph tells me. Know that the sine of 0 is 0. So what I'm going to do first is I'm going to sketch my points before I apply my phase shift and before I apply my vertical shift. So I'm going to sketch my points using my period. I know my period is equal to 4. My amplitude is equal to 2. And then I'm going to use that and kind of graph like a little sketch that'll tell me that. And then I'll apply the phase shift. So I know the sine of 0 is equal to 0. That'll give me a point right there. And if you forget, you can always check, right? You can always check. Let's get rid of these other graphs. What does the graph of regular old sine look like? Here's what the graph of regular old sine looks like. So I start at 0, then I go up, back to 0, down, up, back to 0. That's one full period of sine. So, sine of 0 is 0. Then my next spot, I'm going to go down to -2. because my amplitude is 2. Up to 0. Up to 2. Down to 0. But we actually have 3 things to worry about here. Because remember, our A was negative, which means I need to reflect across the x-axis. So let's do that. Let's apply that reflection. My zeros are going to stay the same place. But this point is going to reflect up here. This point is going to reflect down here. So they're going to swap places. So now I've applied my reflection. And that's what I have. But I also have a phase shift to consider and a vertical shift to consider. So first I'm going to do my phase shift. My phase shift is -1/2. So that means I'm going to pull all my little points to the left a distance of 0.5. So this one, I'm going to pull it over here. This one, I'm going to pull it over here. And over here. And over here. And over here. So I've pulled over every point by 1/2. I'm just erasing these as I go, as I apply each shift. And then I also have that vertical shift of -2. So I'm going to pull down each point a distance of 2. So I'm going to pull this guy down to here. This guy down to here. This guy down to here. This guy. Ooh, am I doing this right? I'll have to check them in a second. This guy down to here. I think I might have messed up. Does this look right? Let's check. I'm checking the distance between each of these is 4. This was at 2 and I pulled it down to 0. That's right. This was at 0. I pulled it down to -2. That's right. This one's at -2. I pulled it down to -4. Okay, I'm happy. I feel good. I hope that you're able to follow as I kind of check myself there. And so now this is our associated sine graph is what we have in blue. And remember that when I pulled all of that down, I also pulled my midline of my graph down to here. Here's my midline. That's important for our asymptotes. So this is our sine. But wait a minute. It's a beautiful sine graph. But what I actually want to graph is not sine. What are we actually graphing again? Let's take a look. We're actually graphing cosecant. So what we can do here is we can take a look at what we have. And I'm going to do this in red so it's really obvious. Everywhere my associated sine graph touches the midline, I have a beautiful asymptote. So I have these asymptotes here. And everywhere that I have a maximum or minimum value, that's where the U for my graph is glued. So it's trapped in between those asymptotes and glued to that blue graph right there. This graph in red is our target all along. And there you have it. There you have it. I hope that this was helpful for some of you. If anything, it's a nice review of how to graph sine and cosine. And now we can use that to graph secant and cosecant. I think the big ticket for you guys is going to be remembering, I know this is the big ticket for me, our identities. That the secant is 1 over cosine. And the cosecant is 1 over sine. Try to remember that, and you'll be able to graph these with no problem. Your textbook takes a slightly different approach to graphing, so you should look through that and see which one you like better. I think this is the easiest way to do it, but you might like the textbook better. I hope you stay safe and well.